I'm Akanksha Chaudhary. I'm an associate research scholar at Princeton. I joined 2 years back, and OpenFOG Consortium had just started at that time, so I got involved right from the start because I had been working on fog computing or edge computing at Microsoft Research, where I was before Princeton. So you know that in the next generation of Internet of Things, video and camera sensors will be dominating a lot of application use cases. Consider traffic monitoring for smart cities, consider video surveillance, consider industrial Internet of Things, assisted driving, connected drones. All of these applications will have camera sensors that can collect a lot of video. And if you try to ship all this video back to the cloud, it can very quickly overwhelm the metropolitan area networks and our existing cloud infrastructure. To give you an example, in 2013, every second someone was uploading 1 hour worth of video to YouTube. If you have 1 million such uploads, you quickly get to tens of terabytes per second, and we don't have that kind of bandwidth available as ingress to our cloud infrastructure. So I got interested in the problem of developing an infrastructure where we did not have to ship all these video back to the cloud, but we could still get the inference that we needed for these next generation Internet of Things applications. My research focuses on a fog computing architecture for video analytics, where the analytics is done closer to where the data is generated. In this architecture, what happens is that the video data is collected at the camera sensor, and then there is a compute node or a hierarchy of compute nodes, which are called as fog nodes. And these nodes both collect the data and draw inferences on it, and then eventually the final set of most expensive inferences drawn back in the cloud. What this allows us to do is solve 3 problems. First, we save on bandwidth, so we don't have to ship everything back to the cloud. So we solve the problem of scarcity of bandwidth. Second, we make sure that we don't use up all the energy on the devices. So we adaptively manage the energy on these fog nodes instead of using up all the energy there. So that's second. And the third aspect is that you ensure low latency guarantees. So there's a long latency if you have to ship everything back to the cloud and get an inference from the cloud. But if you use the fog nodes, which are much closer to where the data is generated, then you have a low latency guarantee, and this becomes important for applications such as drones and connected cars. Computing and storage has become extremely cheap today, and there are a lot of these sensors, so a lot of data is being collected. What that means is that when you collect such kind of data, how do you draw any kind of real-time inference on it? So there is this evolution of fog architectures instead of relying all the way back on the cloud, where you want to be able to analyze the data right where it's generated. And this is very important for video applications specifically, because now we are able to run inference on video data, such as object detection or pattern matching, intruder detection. So all of these are feasible today, but if you have to bring all the data back to the cloud, most often this would be done if there's some incident that has happened, and then you go back and look at the video and figure out when and where that happened. Specific use case being, we collect a lot of videos from traffic cameras today, and even today we don't have good technologies to analyze Amber Alerts. So if you want to find a red car that was Honda Civic and was running down the highway somewhere, oftentimes you still send out a text message and you ask someone to report it, even today, though you have collected all these video. And it would be so cool if we employed fog kind of technologies to be able to automatically analyze and get those answers right away. The way fog computing architecture works for video analytics is that the video is being ingested back wherever the camera sensor is. It could be a traffic camera, it could be a video surveillance camera, it could be a camera in your car, and it could be a camera in your drone. Now, on this ingested video, we want to do some sort of a filtering or some sort of identification of video segments which are relevant to the user. So we identify what type of content would be relevant to the user, and these kind of algorithms would be run back on this fog node. So this is the first set of filtering that has happened. Now, this might mean in a simple scenario that you only selected some cars, video with cars that have red in color. Another fog node might have more compute budget available or more energy available, so it might run more expensive models that are based on deep learning and such, and further drill down this video to smaller set of frames, and then it might at that point go to the cloud where you actually get the answer for the question you posed, which could be an Amber Alert or an intruder detection question. So essentially what is happening in some ways is that you're doing a content-aware compression where you're compressing the video at each level to a smaller and smaller degree based on what content is inside it and what the application cares about. The most surprising aspect is that you would think that shipping all the video back to the cloud, because cloud has a lot more compute power and energy and is able to parallelize things, should be the best solution, but the bandwidth constraints really make it impossible to do that kind of thing, and when you have a large number of cameras, it becomes really impossible. But you can do a lot with even small amounts of compute to really compress the video or filter out the video segments that you care about and then take them back to the cloud, as opposed to taking all the videos back to the cloud. So that was surprising to me, as opposed to, I thought compression was a technology that had been saturated and we had the best compression possible. What was not understood is that most of the compression was developed for not video analytics scenarios, but it was developed for scenarios where you and I are watching TV or internet videos, so we want the entire video. But most of these video analytics scenarios don't want the entire video. They care about certain aspects of the video or inferences from the video.